Hi there, folks. Today we're looking at exponential decay. And just like exponential growth, it's a type of exponential function, but this time we're going to be decreasing. So y is decreasing as x increases. And the reason we don't change the perspective of x is because, again, we're looking at the graph as we go from left to right. Okay, that's x increasing. So exponential growth, as we go left to right, the function goes up. Exponential decay, as we go from left to right, the function goes down. It's decreasing as we go from left to right. As one thing goes up, as x goes up, the y goes down. Okay, we can also determine if it's exponential decay based on the b value. Remember, for growth is when the b value is greater than 1. But if we have a b value that's between 0 and 1, so bigger than 0 but smaller than 1, a proper fraction in between there somewhere, then we're going to have exponential decay. And again, it's that idea that we're decreasing by a certain amount. Well, decreasing by a percentage, as we'll get to later, creates a value that's between 0 and 1. So if I look at something like this guy, again, using our shortcuts and that idea of pattern recognition and what this looks like in y equals a times b to the x, we know that the a value right here acts as our y-intercept. So if I list that as the y-intercept, that's 0, 3. And then the b value, that's what we're multiplying by each time. So that's what I multiply by is the 1/2. And so if I start at 3, and again, I'm just counting towards the left, if I multiply that by 1/2, so I started at 3, times 1/2 is a 1.5. So that goes here. And now 1.5 or 1.5 times 1/2 is a 0.75. And then times 1/2, times 1/2. And so visually, we just keep cutting the value in half. If I go the other way, it's like doubling it. See, I went from 0.75. So if I went from this guy to this guy, that's times 2. Times 2. I can easily work backwards and find the next point, times 2. That's going to be right here. It's going to be a 6. Okay? And so I use that idea of multiplication, and when I do multiplication backwards as division, to kind of work my way back and forth across this function and fill in those values. And again, we're going to get closer and closer to that x-axis, but never actually get there, never actually touch it. Okay? So again, this is exponential decay. I could tell right away by the equation because the b value is between 0 and 1, but I can tell by looking at the graph because the values are decreasing. It's going down as I continue to move towards the right, okay? If I look at this one, again, this one kind of in disguise here, it looks like it might be exponential growth because the b value looks like a 3, but the b value is not actually a 3. And this is a way that we will often express exponential decay, all right? When you get into more complicated exponential models, you might see certain models use negative exponents to determine, to display exponential decay. If I rewrite this, once again, we've got a negative exponent. If I rewrite this without the negative exponent, that'd be 2. If I do 3 to the negative first power, that's a 1/3. Remember, that's what negative exponents do. They flip the fraction, and now I can make this a positive exponent. Okay, so that's what negative exponents do. Now I can see the a value is a 2 and the b value is a 1/2. So again, the a value being a 2, I'm going to use that as the y-intercept. The b value being a 1/3, that's going to be what I multiply by. So times 1/3 each time. Okay, and so coming over here to my graph, I start at the 2. And now I started at 2, and then times 1/3 is going to be 2/3. That's right here. And then times 1/3. It's going to be about here, times 1/3, times 1/3, times 1/3. So this one's getting lower very quickly. If I go backwards, it's times 3. So that can give me another value up here as well. That's going to be the 6. And once again, I get closer and closer to that x-axis, but never actually touch it. Okay? So again, this is exponential decay because the b value is between 0 and 1, and we can see it's decreasing. It's getting smaller as we go. If I look at these guys, determining the type of function and determining if it's exponential. And so if I look at something like this guy, we just look at it and say, hey, what's the pattern? Here the pattern is divided by 3 or times 1/3. And we want to think about it in terms of multiplication. So this one's times 1/3 each time, okay? Yes, it's divided by 3 each time. But we want to think about it from the perspective of multiplication, all right? Because I'm multiplying by the same thing each time, this is exponential. And because the b-value, remember this guy right here, that is the b-value, because the b-value is a 1/3, this is exponential decay. You can also look at this thing and see that it's decreasing. Look at these values. They're going down. They're decreasing. They're getting smaller. They're getting closer to 0. So that also makes it decay. If I look at the next one, once again, I can see that they're decreasing here. I went from 24 to 6 to 2 to 1. So it's decreasing for sure. But I want to determine, is this an exponential function that's decreasing? So I look for that multiplication. And so for this one, to get from 24 to 6, that's divided by 4 or times 1/4. And then to get from 6 to 2, that's divided by 3 or times 1/3. And then it's times 1/2. And so as I look at this thing, yes, there's a pattern in terms of multiplication, but it's not exponential because I'm not multiplying by the same thing each time. Because it's different each time, because it doesn't remain constant. This one's not exponential. Okay, so yeah, it's decreasing, but it's not exponential. Maybe it's linear, so we look and see, no, we're not adding or subtracting the same thing each time. So this is a function that is yet to be determined by us. We're not sure what kind of function this is going to be just yet, but all we know for right now is that it's not exponential at all. Okay, it can't be exponential growth or decay because it's not an exponential function. Okay. And then if I look at the next one, again, I'm multiplying by 1/4 here to get from 32 to 8. And then looks like times 1/4 again, times 1/4. So I am multiplying by 1/4 each time. So that's my b value. I can see the values going down. I can see them decreasing. So this one is exponential decay. All right. It's an exponential function because the pattern is multiplying by the same thing each time. And it's decay because the values are going down. And the b value is between 0 and 1. Okay. Standard exponential decay model is this. For standard exponential decay, it's y equals a times 1 minus r raised to the t. And once again, this is the same kind of thing as the standard exponential growth model, where we talk about it in terms of a percentage. See, before it was a percent increase, so I added the rate. Now it's a percent decrease. I'm decreasing that rate. And if you think back, once again, to how we deal with percentages, okay? When we deal with percentages, like if I said something was 20% off the original price, you would take 100 minus 20 because we start with 100%, we take away 20%, that gives us 80%, and then to find 80% of something, we multiply by that 80%. And so that's the idea here, all right? The rate, the decay rate is telling me, hey, I'm going to subtract a certain amount, okay? But I'm going to subtract in terms of percent, which means I need to subtract that from 100 and then multiply by that thing. And so again, that 1 minus r is the b value. It is what we're multiplying by, but from the perspective of percentages. So the decay rate, once again, it's a percent decrease. And we have to write it as a decimal. Okay, so percent decrease as a decimal. And again, it's the same way we dealt with percentages originally. Okay, if I want to take a certain percent off, I do 100 minus that and write it as decimal. Well, that's the effect that the 1 minus r has. It's essentially doing the same thing. So if I had a rate of 20% that it was decreasing by, I would do 1 minus 0.2 and get a 0.8, the same way I would before. The 0.8 becomes the thing I'm multiplying by over and over again. Okay. For example, if I look at something like this guy, it says a brand new car costs $32,000 and depreciates. That means it decreases in value. It loses value at 22% per year. What will the car cost in 4 years? And so once again, if I use this, it's y equals a times 1 minus r raised to the t. And I start with what I know. The initial amount, what I start with is $32,000. The rate this time is 22%, but I have to write that as a decimal. So that's 0.22. And now the time is 4 years. And once again, just like exponential growth, I have to make sure the units match. This was per year. This is in years, so we're good to go. And I'm going to do one step by hand, and then we'll plug it into the calculator. So the one step I'm going to do by hand is that subtraction. Well, if I subtract those, well, that's 78%, 0.78. And again, it's the same thing that we deal with when we're dealing with percentages. I start with 100% and I take 22% off. That leaves me with 78%. That's what I'm multiplying by, okay? And now I can see this in the format of y equals a times b to the x, all right? And b, that's 78%, that 0.78, that's what we're multiplying by, okay? And remember, once again, when you punch this in, make sure you do the 0.78 raised to the fourth power first, then times the 32,000. And you get 11. Oh, let me give myself a little bit more space here, so I can write my money symbol. $11,844.82. And again, always round to 2 decimal places when we're talking about money, okay? And when you look at that, you're probably looking at that going, 4 years and it's down that much? Yeah, certain things depreciate a lot faster than others. Cars are one of those things because they take a lot of abuse, okay? Every time you drive a car, you're essentially making it worse, okay? As you drive it and things get worn and that kind of stuff, the tires get worn and, you hit potholes. So they depreciate very quickly, okay? Something like this guy, it says from 1963 to 2002, the number of acres of ponderosa pine forest decreased by 0.5% annually. If there were 41 million acres in 1963, how many acres remain in 2002? And so if we look at this thing, first of all, from 1963 to 2002, we have to look in how many years that is. So we have to take the 2002 minus the 1963, and we see that that's 39 years. That's going to be important because when we plug things into an equation, we don't plug them in terms of years, in terms of the dates. We plug it in terms of number of years that has passed. So let's make a note to self over here. That's 39 years. Okay, and then also be careful here. It looks like this guy is already written as a decimal, but it's not. It's still written as a percent. So when we write this guy as a decimal, it's 0.005 for 5%. So be careful with some of those things. Make sure you're plugging these in correctly. Make sure you're converting these things the way they need to be converted. And now that's an annual rate. We've got years and years, so all the units match. So let's set up our equation. Y equals a times 1 minus r raised to the t. Okay? And so here, the initial amount was 41 million. I'm just going to leave it as 41. I'm not going to write all the zeros there. If it's written as 41 here, we can do the calculations of 41. We just have to tack on that designation of millions when we're done. And now 1 minus, that's 0.005, that's 5%. Raised to the t, which is the 39 years, okay? And so just be really careful how these things are expressed. Make sure that the units match, that kind of stuff. And once again, I'm going to do one step by hand here. Oh, I started to write it instead. That's going to be a 0.995, okay? If I had 100%, I take away 0.5%. I'm at 99.5%, which is 0.995. And I'll raise to the 39, okay? And once again, as you punch this into your calculator, make sure that you do the 0.995 raised to the 39th power first, okay? You have to do that first and then multiply by the 41, okay? The other thing is, if you punch this in exactly the way it's written with those parentheses and everything, it will work just fine. Your calculator will interpret it correctly. And so I get 33.7, and again, that's million. Okay, so make sure you slap that designation back on there. It's not 33.7, it's 33.7 million, okay? But again, when you're looking at exponential decay, we're talking about subtracting a percent decrease, which is why we subtract that value, okay? That's why it's minus the r, all right? And so again, exponential decay, it's the same as growth, except now the values are decreasing. The b values between 0 and 1. They're all still exponential models. It's just how do we interpret those exponential models, okay?